discussing Jitendra Malik's presentation he recently gave with the title, Will We Have Intelligent Robots? Malik is one of the pivotal figures in robotics. He's a professor at Berkeley. And I would say his presentation is one of those pivotal moments in robotics because, in a nutshell, what he's saying is that transformer architectures will be the future of robotics, and that the problem is data, which is not new, but he has a solution which is 3D video, and that to me is news. So I think those two are really the fundamentally new ideas that he's conveying in this talk. There's a couple of papers he's presenting, in particular one where they use robotics, formulate robotics as a token prediction problem, which is, to me, is it's not new in a sense that I was expecting this, but to come from such a high caliber personality, I think it validates the concept. So I'm going to go through the talk and particularly focus on the so-called Moravec's paradox, which is hard tasks are easy and easy tasks are hard. Well, like as usual with paradoxes, there's no such thing as a paradox. There's a truth behind it, which is simply that playing chess and Go is actually a not so interesting activity. Writing code is not an interesting activity. Humans should not do this. What's interesting is creativity, multimodal, large Hilbert space type activities where the dimensionality is much higher, whether this is athletics or math or things like that, or arts, where you're not constrained into a very narrow rule set, but you have a lot more degrees of freedom. So Moravec's paradox is really not a paradox. Moravec is just saying that some of the we humans were just wrong, thinking that passing a law degree exam is hard is wrong, and I think we all intuitively knew that those types of exams are nothing more than tests to pass a test. Playing chess has never been interesting to me, even as a player, actually. And then let's go further with Go and all that. The same thing. So anyway, the point here is that like what are we actually trying to do, right? We want to create, in the end, what we want to create is a Robinson Crusoe robot. Now Malik's not talking about that yet. What I call unsupervised intelligence is not this talk is really just about, okay, we're not going further into Douglas Hofstadter territory where robots develop their eye and the loop starts looping in a human way, where the robot starts even formulating its own purpose and things like that. We're just trying to build a robot. We're trying to build a self-driving car here. That's what we're really trying to do at Orange Capital Partners. We're invested in Tesla. We want to build a foundation model for embodied decision-making agents. That is part of the game, and this is part 13 of our series on foundation models for embodied decision-making agents. And I think this part 13 is really pivotal because it is actually coming from one of the most important players in the space, Jitendra Malik, and he's validating the concept. So what is he doing here is going through general ideas, control theory versus pattern recognition. He talks about this, and then he's going to talk about a couple of papers. This is not in our podcast. It's April 11, 2024. This is Crindelco. For the day, the fund is up 90 basis points. The market is flat. For the year, we are down 18.3%. The market is up 7.6%. We're underperforming by 25.9%. Jitendra Malik's talk, named When Will We Have Intelligent Robots, is, like I said in the prelude, a really important pivotal talk because he's launching, let me call it this way, I think this talk is launching the era of transformers for robotics, once and for all. Coming from a research group of this caliber, I think will definitely put everything, all critics to rest. This is the future. Now, how exactly this will be done and whether we will have a similar architecture like in large language models, which is pre-training and then fine-tuning through RL. We'll see about that. But let's go through the talk and then discuss some of the main points. So we want AI agents that can discover like we can, not which can contain what we have discovered. Richard Sutton. So this is just a quote to launch the talk, and the idea is it goes back to Turing also, which is also mentioned in the talk. We don't want to, build systems that learn what humans know, but we want to build systems that learn how children learn. It's about learning. It's about the loop. It's about data-driven pattern recognition and then optimization. So I would say I already mentioned Moravec's paradox in the prelude. Again, it's not a paradox. Tasks that are hard to program, or program is the wrong word. Tasks that are hard for robots are just hard tasks. It's not like we humans don't know how to do it. There's hard stuff and there's easy stuff. According to Jitendra Malik, the reason we find it hard to have a robot make scrambled eggs and we find it easy to have a robot play chess, it just goes back to the data pipeline. If we had enough data about scrambled eggs making, and what that means is not just video data per se, which is the most, it's sort of the go-to type data format. What he means with that is we should have, data about the actuators, our joint position, our forces that we use. Well, we don't have any of that stuff. So and that's why it's hard. Versus in LLMs, we do have a lot of data, and that's why we can use transformers. Jitendra goes back to the history of intelligence and then kind of just makes the point that language came really very well towards the end of development, meaning if the Big Bang is not the Big Bang, if life is 24 hours, then language came in the last 3 seconds or something like that. So we had many percent, 99.999% of development of intelligence on Earth has been driven by all kinds of other things and not language. So language is very recent, and Moravec's paradox is trying to be explained by people. Well, it's just because it's recent that it's not very well developed, and therefore we can do it as humans. That's not true. It's just simply, it's the internet. We have the data, which is really what makes us, the Orange Capital Partners, very bullish on Tesla, because Tesla is the only company which has internet scale data on video. Now, one of the main arguments in this talk is that we need to 3-defy video, that this is key. This is fundamentally key. And I just recently attended a talk at Stanford about that, 3-defying a video. This is becoming a massive problem to be solved. And the reason this is important, it's on the one hand important for things like VR and AR, but it's a lot more important for robotics. And what's really exciting here, the way we see this develop, is because AR and VR will push for 3-defying 2D images, we will actually have a side effect, which is this ability to robot learn. And this is one of those things. This is compound. This is what I mean when I talk about compound returns on technology. You 3-defy 2D images, and then you create a robotics fleet. The robotics fleet can compound on its own data and create a massive internet scale data set with 3-defy 2D images and video, and hence you can build transformer architectures and solve robotics. This is what I mean with compound. So what is let me go through some of the papers that he's talking about. Rapid motor adaptation for legged robots. This is a paper that Malik introduces just to bring the concept home that end-to-end learning actually works for robots. This paper was published in, I think, 2022. So this is pretty much when Tesla starts talking about end-to-end. So I can see a relationship here between end-to-end and Malik's research. I feel like Malik's research is actually this paper came out in 21. So this is definitely, I would say, an inspirational paper. just bringing home the concept that you can have end-to-end learning. By the way, before I go paper discussion, I just want to talk a little bit about control versus pattern recognition. He talks about this. So what does it mean? So we have traditional control theory, which is x naught equals matrix A times input x plus some sort of control factor bu. Now, the matrix AX is analytically derived in traditional control theory. That's what control theory is. So you have an input, and then you transform the input into something x naught, and that's control theory. So the robot has a bunch of actuators which are captured in the matrix A. It gets an input. Let's say this is your scene. Now do something. It transforms the actuators and does stuff. What this new area of deep learning does, it still uses pattern recognition and those sort of things. But what it does, it learns the matrix A, and the matrix A adapts to the environment. And then he also talks about latent space, which is another part of the equation. So think about it this way: you have a translation matrix A, which learns how to change. Take the self-driving car. The self-driving car learns how to deal with actuators and things like that. But it also has a latent space representation of the world, which the car uses to learn. So in other words, latent space representation, some sort of low dimensionality that Malik really tries to bring across. We can reduce the real world into low dimensionality and then use that information to navigate through the world and adapt. So what that means is a slippery road is perceived different than a non-slippery road. The robot can learn end-to-end what that means. The robot doesn't have to know what it means to be slippery. It doesn't have to have the physics understanding of what it means to be wet. All it needs to understand is that when the road is wet, the actuators need to change. So let me just jump to the sort of main paper here, which is humanoid locomotion as next token prediction. In this paper, we cast humanoid control as data modeling of large collections of sensory motor trajectories. Like in language, we train a general transformer model to autoregressively predict shifted input sequences. In contrast to language, the nature of data in robotics is different. It is high-dimensional and contains multiple input modalities. Different modalities include sensors, like joint encoders or inertial measurement units, as well as motor commands. These give rise to sensory motor trajectories, which we view as the sentences of the physical world. Adopting this perspective suggests a simple instantiation of the language modeling framework in the robotic context. We tokenize the input trajectories and train a causal transformer model to predict shifted tokens. Importantly, we predict complete input sequences, including both sensory and motor tokens. In other words, we are modeling the joint data distribution as opposed to the conditional action distribution. So what does this really mean? So they're looking at observation and action as not one is conditional on the other. They're just looking at the history of those pairs. And they're trying to predict the next history action tuple going forward. This is, in a nutshell, what they're doing, which to me is really, I haven't heard robotics people talk like this before. This is new. And I sense this is going to be really interesting at CVPR this year, to hear people talk about this. To me, this is fundamental. This is really, really interesting. So again, we tokenize the input trajectories and train a causal transformer model to predict shifted tokens. Importantly, we predict complete input sequences, including both sensory and motor tokens. In other words, we are modeling the joint data distribution as opposed to the conditional action distribution. What's the role of reinforcement learning? The role of reinforcement learning is optimization. It goes back to Sergey Levin, right? We have pattern recognition, this joint data distribution between observation and action. Think of it like a massive data set of states and action, state action, state action. But then we also use reinforcement learning to find the most optimal trajectory. Reinforcement learning, or the most bang for the buck, as Malik calls it, is reinforcement learning gets you adaptation. This is the key, okay? So you have two problems in optimization. One is find the best trajectory. So you're given a massive amount of observation action tuples. You use transformer architecture to predict the next token, but to find the most optimal trajectory, you can use reinforcement learning. And reinforcement learning gives you two big advantages. One, it goes through the search space of actions that could be used given the next observation that you see, but it also adapts. So the bang for the buck comes from adaptation. So to summarize, this talk is pivotal. It's fundamental. It's one of those talks that I think will change robotics for the good. The three main takeaways are bang for the buck in RL comes from adaptation. So if you go back to traditional control theory, you have X naught equals matrix A transforming the input X plus some regularization BU. And that matrix A is learnable. And RL can not just learn a good trajectory through search, it can also have adaptation. And that's the key, adaptation. Second, the concept of robotics in 3D-defined 2D images. So key concept for robotics is 3D-defined 2D images, so robots can learn from video. This is compound bilayer technology. This is the same way when computer vision came along, it enabled self-driving cars. I think I want to press this point one more time, and it reminds me actually of Neil Shubin's book about the transition from water to land, which a couple of years ago I talked about. It really struck me because what it says there is that when species conquers new territory, in other words, when evolution finds new niches, when new technology is developed to survive in new biotopes, then often this transition is actually happening in a linear fashion, even though it might sound really crazy. Like, how did you go from swimming in the water to conquering land? Well, what happened is there were ingredients that might not have been very useful in the water, but they were developed for whatever reason, particularly maybe for species that wasn't very competitive in the water. They had to develop, something akin to limbs just to crawl on the ground, so they don't have to compete with sharks and things like that. And that became very useful on land, and hence, lo and behold, they conquered land. So the same here is like you have these ingredients, like for example, convolutional neural nets. They enabled vision, and vision enabled self-driving cars, and self-driving cars are now collecting a massive amount of data for robots to move around nature. If we can solve 3D-defined 2D images, we can use that to solve robots, because while a self-driving car doesn't necessarily have to 3D-define the world, a robot does, particularly the grasping problem of robots. But in general, you want to know what's the 3D nature of stuff when you're going around in the real world. And the same, by the way, applies to things like, what's a slippery road? In general, physics is going to be much, much better understood by end-to-end networks if they can 3D-define. So this is, one ingredient's necessary for the other. I think this is really key, and Jitendra's talk reminds me of that. I think that's the point he wants to make, and that's why I consider this talk a pivotal talk, really one of those massive, important talks that we will go back to in the past, in a few years, and say this was when the air when the area got a huge boost. Now, for us, Orange Capital Partners, this is really important. I have to bring this across. The purpose of this podcast is to give people a sense of what it feels like to run a hedge fund. This is what we do. We spend a lot of time with the science, whether it's at NeurIPS or CVPR or Coral or any of those conferences. We go to universities here in the Bay Area to see where the science is going, where that Venn diagram between science and technology and entrepreneurship could be. And we identify this, and this is now very important, let's say, for Tesla. Tesla has, in my opinion, solved self-driving car problem to the extent that the agent is able to move around in nature. Maybe not fully, but that's okay. Now the next step for the humanoid robot, to use this robot in a factory setting, for example, is going to be 3D 2D images. Create a fleet of robots that is trained on video data, and then use that data from the fleet of robots, again, 3D that video data from the robots themselves. So you don't even have to 3D that necessarily, because the real data from the robots will be in 3D already. But you can then build on that and create a massive robot fleet. This is beautiful. This is beauty in a nutshell. It's elegant, it's beautiful, it's simple. And just to finish, I think, shout out to Jitendra Malik. He has this uncanny ability to formulate very difficult, very complex concepts in very simple words. Just read his papers. Next token prediction for robots. We use state action pairs, not as a conditional data set, but as a just a distribution data set, like language models do. We look at patterns, and then we use reinforcement learning to optimize the trajectory and also optimize in an adaptive way. This is the beauty. It's simple, it's understandable, you can explain it to your mother, and that's how science progresses. Thank you.